Now let's zoom in on what we're actually going to build. It's called the Employee Management System, and it's a simple program that helps you organize information about managers and developers. Instead of juggling separate notes or lists, you'll be able to add new employees, see everyone's details in one place, and even search for someone by their ID, all from one console app. When you run the program, it starts by showing you a menu with numbered options like Add Manager, Add Developer, View All Employees, or Search Employee by ID. For example, if you choose option 1 and type in a manager's name, ID, salary, and team size, the program will confirm that the manager has been added. Then you can choose to view all employees and instantly see their information displayed neatly on the screen. Along the way, you'll practice some core Python concepts, how to build and use classes, how inheritance lets you extend a class to create new ones, how polymorphism allows the same method name to behave differently depending on the object type, how to collect user input with input, how to store objects in a list, and how to use loops and if-else conditions to control the flow of the program. By the end of this lesson, you'll not only have a working employee management system, but also a clearer understanding of how classes, inheritance, and polymorphism can organize real-world data in code. In the next step, we'll go through the code together line by line and see exactly how it all works. Okay, let's take a look at the overall structure before we dive into the actual code. On the left, you can see the class definitions for employee, manager, and developer. Each class already has placeholder methods and print statements showing where we'll initialize data and where we'll display information. This gives you a clear roadmap of how attributes and methods will work, and how inheritance ties the classes together. On the right, inside the main function, you can see the menu system set up with options for adding managers or developers, viewing all employees, searching by ID, and quitting the program. Each choice has a placeholder print statement that tells you what logic will eventually go there, such as collecting input, creating objects, or looping through the list of employees. This approach helps you focus on understanding the flow first. Classes, inheritance, input collection, storing objects in a list, and controlling the program with loops and conditions. Once the structure is clear, you can then go back and fill in each section with the actual code. Okay, let's take a look at them one by one. We start with the employee class, which is our base blueprint. Its initializer sets up 3 pieces of data for every employee, a name, an ID, and a salary. The keyword self simply means the specific object I'm building right now. So when we assign values to self-name, self-employee ID, and self-salary, we're storing data inside that one object. The show_info method is a simple printer. When called, it reads those stored values from the object and displays them in a single tidy line. Next up is manager, which inherits from employee. You can see that in the class header, where manager lists employee in parentheses. That means manager gets all the core features of employee for free. Inside the manager initializer, we accept the same pieces of data as employee plus 1 more team size. We immediately call superInit to let the employee class do its normal setup before adding manager-specific data. This order matters. Initialize the base first, then extend with anything unique to the child class. In showInfo method for manager, we reuse the parent's printing by calling super showInfo method, and then we add 1 extra line that labels the role as manager and shows the team size. This is a good example of extending rather than rewriting, less duplication, and easier maintenance if you later change how the shared info is displayed. Then we have developer, which follows the same pattern. It inherits from employee, calls superInit to set up the shared fields, and then stores an additional attribute called language. Its showInfo method again calls the parent's version first to print the standard details, and then adds a second line that labels the role as developer and shows the programming language. This call the parent, then add what's special technique gives you a consistent output format across roles and keeps your code DRY, don't repeat yourself. Stepping back, this slide shows 4 key ideas in action. A class groups related data and behavior so you can model something from the real world cleanly. Inheritance lets a specialized class reuse and extend a general one, which removes duplication and keeps your design organized. Super is your bridge to the parent class. Use it in the initializer to ensure the base attributes are set up, and in overridden methods like showInfo method when you want to add to not replace the original behavior. And finally, polymorphism is at work here. Even though we call the same method name showInfo method on different types of employees, Python automatically picks the right version for each object. With these pieces in place, you have a flexible foundation that plugs neatly into the menu-driven app and makes it easy to add new employee types later if you need to. Okay, let's take a look at both of these options together. These two sections of code handle what happens when the user chooses option 1 to add a manager or option 2 to add a developer. The structure of each block is almost identical. The only difference is the extra piece of information we ask for and the type of object we create at the end. First, the program uses input to ask the user for details. For a manager, we collect the name, ID, salary, and team size. For a developer, we collect the name, ID, salary, and primary programming language. This is how the program interacts with the person running it, turning their answers into data we can store. Next, we create a new object from the right class, manager or developer. This step takes the values the user typed and passes them into the class initializer. It's like filling in a form and producing a completed card at the end. The card here is the object that holds all of the employees' details. Then we use employees.append to add that new object to our main list. This keeps everything in one place, so later options like viewing all employees or searching by ID can access the information easily. Finally, a quick print statement confirms the addition by name, giving feedback to the user. Looking at both blocks side by side, you can see the same pattern. Collect input, create an object, append it to the list, and confirm it. Once you understand this pattern, you can adapt it to handle any new employee type or extra information you want to add in the future. Okay, let's take a look at this section. This part of the code runs when the user chooses option 3 from the menu to view all employees currently stored in the system. It starts by checking whether the employees list is empty using the phrase "if not employees." This is a handy Python shortcut for saying if the list has no items in it. If it's empty, the program simply prints a message telling the user no employees are found. If the list isn't empty, the program prints a header line so the user knows they're about to see all the data. Then it uses a for-in loop to go through each object inside the employees list one at a time. For every employee object, it calls the showInfo method. This triggers the code inside each object's class to display its details neatly. This block shows how to combine a condition to check for data, a loop to go through that data, and a method call on each object to get its information. It's a simple but powerful pattern that makes your program dynamic. No matter how many employees are stored, it will automatically display them all without extra work. Okay, let's take a look at this section. This code runs when the user chooses option 4 from the menu to search for an employee by ID. It starts by asking the user to type in the ID they're looking for using input. That value is stored in search ID, so the program can compare it against the IDs of all employees we've already saved. We then set a variable called found to false. This acts like a flag to keep track of whether we've matched anyone yet. Next comes a for-in loop that goes through each employee object in the employees list. For every object, we check its employee ID attribute to see if it equals the search ID. If it matches, we immediately call that object's showInfo method to display its details. At the same time, we set found to true and break out of the loop, so we stop checking further once we've located the right person. Finally, if the loop finishes without finding any matches, found stays false, and the program prints employee not found. This block demonstrates how to access an object's attribute directly, how to call one of its methods, and how to combine a loop and a flag to search through a collection safely. Once you understand this pattern, You can adapt it for any kind of search or filtering feature in your own programs. Okay, let's finish up by looking at the quit option. This part of the code runs when the user chooses option 5 from the menu. All it does is print goodbye to let the user know the program is ending, and then it calls break. The break statement immediately stops the while loop that keeps the menu running, which effectively ends the whole program. If the user types in something that doesn't match any valid option, the else part at the bottom kicks in and prints invalid choice. This gives the program a clean way to handle mistakes without crashing. Now that we've gone through each section of the code, in the next part we'll move on to the demo and see the whole program running from start to finish. Let's quickly run through how it looks when this program runs. When you first start the employee management system, it shows a menu with 5 options. You type 1 to add a manager, and the program asks for the manager's name, ID, salary, and team size. You enter Tom M001 50,005, and the program confirms with a message that Manager Tom has been added. Back at the menu, you type 2 to add a developer. The program then asks for the developer's name, ID, salary, and primary programming language. You enter Alice D001 50,000 and Python, and the program confirms that developer Alice has been added. Next, you type 3 to view all employees. The program displays a heading All Employees and shows Tom's information with his role and team size, followed by Alice's information with her role and language. Back at the menu, you type 4 to search for an employee by ID. You enter D001, and the program immediately displays Alice's information, showing that it found the correct employee. Finally, you type 5 to quit. The program prints goodbye and ends cleanly. This sequence shows how each feature flows naturally and how the program responds to your input step by step. Let's take a look at how the program handles errors and unexpected input. These little checks are what keep the app from breaking and guide the user instead. First, I choose option 3 to view all employees. Because the list is empty, the program immediately shows no employees found instead of printing nothing or throwing an error. This is our first layer of error handling. It checks if the list is empty before trying to loop through it. Next, I choose option 4 to search for an employee by ID and type Tom. Since no employee with that ID exists, the program politely responds with employee not found. This prevents confusion and lets the user know they either need to add the employee or check the ID. Finally, I enter an invalid menu option number 6. The program doesn't crash or do something unexpected. It simply says invalid choice. This is another small but important safeguard, making sure the user only selects valid options. Together, these checks make the app more robust and user-friendly. They're simple conditions, but they demonstrate the basic idea behind error handling. Always verify your data and give clear feedback when something isn't right. That's it for this project. You've just built a simple but powerful employee management system that lets you add managers and developers, view everyone in one place, and search for a specific employee by their ID. Along the way, you practice some key Python skills, creating and using classes to model real-world data, applying inheritance to avoid repeating yourself, using polymorphism, so the same method name can behave differently for managers and developers, collecting input from users, storing objects in a list, using loops to process data, and writing clear conditions to handle errors and guide the flow. Great work! Try experimenting with new features or adding other employee types and see how far you can take it. See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is straightforward. It asks the user to enter their weight and height, calculates their body mass index, and then tells them which health category they fall into, such as underweight, normal, or overweight. At the same time, the program makes sure that incorrect inputs like 0 or negative numbers are handled safely so the app never crashes. When the program runs, it looks clean and easy to follow in the terminal. You'll see a short title, then a prompt asking for weight in kilograms and height in meters. For example, if the user enters 65 for weight and 1.7 for height, the program immediately shows the calculated BMI and prints a clear category like normal. If the user enters something invalid, the program responds with a helpful message instead of an error wall of text. While building this app, you'll practice several core Python concepts that every beginner needs. You'll use input to collect data from the user, variables to store values like weight and height, conditional statements to decide which BMI category to show, try and accept to handle errors gracefully, and a loop to allow the user to calculate again without restarting the program. This project is a great example of how small programs can still feel polished and useful. You're not just writing code that works, you're writing code that thinks about the user experience. In the next step, we'll walk through the program line by line and build it together so you can clearly see how each part works. Now let's look at the structure of the program and understand how everything fits together. At the top, we define a function that handles the BMI calculation. This function is responsible for showing a title, asking the user for weight and height, calculating the BMI using a simple formula, and printing the result. Keeping this logic inside a function makes the code easier to lead and reuse. Next, we have the main control flow of the program. A loop keeps the application running so the user can calculate BMI multiple times without restarting the app. After each calculation, the program asks whether the user wants to continue or exit, and based on that input, it either repeats or ends cleanly. At this stage, the program works, but it is still incomplete. It only shows the BMI number, and it does not explain what that number means. It also assumes the user always enters valid values, which is not realistic in real applications. In the next step, we are going to improve this structure by adding health categories. This will allow the program to interpret the BMI value and clearly tell the user whether they are underweight, normal, or overweight, making the output much more meaningful and user-friendly. Now that the BMI calculation is working, let's zoom in on how we turn that number into something meaningful. A single BMI value on its own can be hard to interpret. So in this step, we add simple logic to classify the result into clear health categories. Here, the program checks the BMI value and compares it against standard ranges. If the value is below 18.5, it shows underweight. If it is below 25, it shows normal. If it is below 30, it shows overweight, and anything above that is classified as obese. This is done using an if, elif, and else structure, which lets the program make decisions based on conditions. When you run the program now, you still enter your weight and height the same way, but after the BMI is displayed, you also see a category printed right below it. For example, entering a weight of 65 and a height of 1.7 shows a BMI around 22 and a normal category, while a shorter height might result in an overweight or obese category. This step is important because it shows how simple conditional logic can turn raw numbers into useful feedback for users. It also makes the app feel more complete and realistic. In the next step, we will make the program more robust by adding error handling, so it can safely deal with invalid inputs like text, negative numbers, or zero values without crashing. Now let's focus on error handling and why it's such an important upgrade for this project. So far, our BMI calculator works well when the user enters correct values, but real users don't always do that. They might type letters instead of numbers, enter 0 for height, or use negative values by mistake. Without error handling, any of these cases would cause the program to crash, which is a bad experience for users. To solve this, we wrap the input and calculation logic inside a try block. This allows the program to attempt the calculation safely. If something goes wrong, Python immediately jumps to the appropriate except block instead of stopping the program. Here we handle multiple types of errors. If the user enters text instead of a number, a value error is triggered. and we display a clear message explaining what went wrong. If the user enters 0 for height, we raise a 0 division error manually and show a specific message saying that height cannot be 0. We also check for negative values and raise meaningful errors before the calculation happens. When you run the program now, invalid input no longer breaks anything. For example, entering 0 for height prints a clear error message, entering a 0 or negative weight shows another message, and entering letters instead of numbers is handled cleanly. The program stays stable and user-friendly. That's it for this project. We've built a simple but practical BMI calculator that takes a user's weight and height, calculates their body mass index, and then explains what that number means with a clear health category. Through this project, you've practiced several core Python concepts that are essential for beginners. You used input to collect data from the user, variables to store values, mathematical operations to perform calculations, and conditional logic to decide which health category to display. You also learned how to use try and except to handle errors safely, how to raise your own errors for invalid input, and how a loop can keep a program running until the user chooses to exit. This project shows how even a small console app can feel complete, reliable, and user-friendly when the right ideas are combined. Great work! Try experimenting with your own improvements and see you in the next lesson. Now let's zoom in on what we're actually going to build. In this project, we're creating a Notes app, a simple but very practical Python console application that helps you save and lead short notes directly from the terminal. The goal of this program is to give you an easy way to write down ideas, reminders, or study notes and keep them stored safely. You can add a new note, view all your saved notes, and exit the app whenever you like. Everything is saved automatically, so when you run the program again later, your notes are still there. When the program runs, you'll see a clean menu in the console with 3 options. For example, you might choose option 2 to add a note, type something like study Python file handling, and immediately see a message confirming that the note was saved. If you then choose option 1, the program displays all your notes in a simple list so you can review them anytime. Along the way, this project introduces several core Python concepts. You'll use input to get information from the user, variables to store data, and a while loop to keep the menu running until the user decides to exit. You'll also learn how file handling works, how to lead and write text data, and how try except helps your program handle errors safely instead of crashing. This is a great beginner project because it shows how small pieces of Python come together to form a complete usable application. You're not just learning syntax, you're building something real. In the next step, we'll walk through the program logic step by step and see exactly how each part works together. Now let's take a look at the structure of this program and how everything is organized. At the top, we prepare the basic setup, including where the notes will be stored. Then we define separate functions for each action the user can take. One function is responsible for showing saved notes, another handles adding new notes, and the main function controls the menu and keeps the app running. The main function uses a while loop to repeatedly show the menu and wait for user input. When the user selects an option, the program checks the choice and calls the correct function. This is a very common and important pattern in console applications, and you'll see it again and again in real projects. With this structure in place, each part of the program has a clear purpose. That means we can focus on one feature at a time without getting overwhelmed. In the next step, we'll zoom in on the add note function and see exactly how a user's input is saved step by step. Now let's focus on how adding a note works. This is the part of the app where the user actually creates new content and saves it for later. When the user selects the Add Note option from the menu, the program first asks them to type their note. Whatever they enter is temporarily stored so we can check it before saving. To avoid useless or accidental entries, the program removes extra spaces and checks if the input is empty. If the user just presses enter without typing anything, the program immediately shows a clear message and stops the process there. If the note contains real text, the program then opens the notes file in append mode. This is important because it means new notes are added to the end of the file instead of overwriting existing ones. The note is written as a new line, saved automatically, and the user sees a confirmation message so they know everything worked as expected. This small function teaches an important lesson. Even simple features need validation and careful file handling to behave properly. By keeping this logic inside its own function, the code stays clean and easy to understand. With adding notes covered, the app already feels useful. In the next step, we'll look at the view notes function and see how saved notes are led from the file and displayed back to the user. Now let's look at how the app shows saved notes back to the user. This part is handled by the view notes function, and it's where file reading and error handling really come together. When the user chooses the View Notes option, the program first prints a clear header so it's obvious we're switching into note viewing mode. Then it tries to open the notes file in LED mode. If the file exists and contains text, the program reads everything inside and displays it exactly as it was saved, line by line, so the user can quickly review their notes. There's also an important check here. If the file exists but doesn't contain any real text, the program doesn't just print a blank screen. Instead, it shows a friendly message saying there are no notes yet, which makes the app feel much more polished and easier to understand. If the file doesn't exist at all, the program handles that situation safely using try except. Rather than crashing, it explains what happened and tells the user to add a note first. This is a great example of defensive programming, where we expect things to go wrong and handle them calmly. That's it for this project. In this lesson, you built a simple notes app that lets users write short notes, save them, and lead them back later using a Python console program. Through this project, you practiced several important Python concepts. You used input and print to interact with the user, variables to store data, and a while loop to keep the menu running. You also learned how file handling works for saving and reading text, how string cleaning helps validate input, and how try except allows your program to handle errors safely. This is a great example of how small pieces of Python come together to create a complete and useful application. Try extending it by adding new features or changing how notes are displayed. Great work! See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is straightforward and beginner-friendly. The computer generates a random number between 1 and 100, and the user keeps entering guesses. After each guess, the program responds with helpful feedback, telling the user whether the guess is too high or too low. The game continues until the correct number is found, and it even keeps track of how many attempts it took and asks if the user wants to play again. When the program runs, it starts by printing a message like, "I'm thinking of a number between 1 and 100. The user then types a guess, for example 50. If that guess is incorrect, the program immediately responds with something like too high, try again. The user guesses again, maybe 25, and the program responds too low. This back and forth continues until the correct number is entered, at which point the program displays a success message showing how many attempts were needed and then asks whether to restart or exit. Along the way, this project introduces several core Python concepts. You'll use input to receive user input, variables to store the secret number and attempt count, and while loops to keep the game running until the correct guess is made. You'll also use if, elif, else statements to compare guesses and provide feedback, try except to safely handle invalid input, and the random module to generate unpredictable numbers. This is a great project because it shows how simple Python tools can come together to create something interactive and fun. You're not just writing code that runs once. You're building a program that reacts, guides the user, and feels like a real game. In the next step, we'll walk through the code piece by piece and see exactly how each part works in a clear, step-by-step example. Next, let's look at the structure of our program and focus on creating the guess number game function. This function is where the actual game logic lives, so you can think of it as the heart of the application. Inside this function, we start by printing a welcome message and explaining the rules to the user, such as letting them know the computer is thinking of a number between 1 and 100. This helps set the context every time the game starts and makes the program feel friendly and clear. After that, the function asks the user to enter a guess. We lead that input from the keyboard, convert it into a number, and store it in a variable. This is an important step because it shows how a program can pause, wait for user input, and then continue running based on what the user typed. At this stage, we're not worrying about repeating guesses or checking whether the number is correct yet. The goal here is simply to build a clean, reusable function that handles one round of interaction. By putting this logic inside guess number game function, we make the code easier to lead, easier to test, and easier to extend later. This structure also prepares us for the main loop, where the game can be played again and again without restarting the program. In the next step, we'll expand this function and add the logic that compares the guess, gives feedback, and keeps the game running until the correct number is found. Now let's take a look at the structure of this program and how everything is organized. Next, we complete the core of the game by fully building the guess number game function. This is where everything comes together and the game truly comes to life. At the start of this function, the program generates a secret number using Python's random module and stores it in a variable. It also initializes an attempt counter, which allows us to keep track of how many guesses the user makes. These two variables set the foundation for the game logic. The game then enters a loop that keeps running until the correct number is guessed. Inside this loop, the program asks the user to enter a number and safely converts that input into an integer. Each valid guess increases the attempt count, helping us measure progress as the game goes on. Once a guess is entered, the program compares it with the secret number. If the guess is smaller, it tells the user the number is too low. If it's larger, it responds that the guess is too high. When the guess finally matches the secret number, the program prints a success message showing how many attempts it took and exits the loop, ending the round. This function also demonstrates safe input handling. If the user enters something that isn't a number, the program doesn't crash. Instead, it catches the error and politely asks the user to enter a valid number, then continues the game smoothly. That's it for this project. In this project, you built a guess the number game, where the computer thinks of a number and the player tries to figure it out by making guesses. With each guess, the program responds with helpful feedback, guiding the player closer to the correct answer until the game is finally solved. Along the way, this project demonstrates several important Python concepts. You practiced using input and output to interact with users, variables to store values like the secret number and attempt count, and while loops to keep the game running. You also used if and else logic to compare guesses, the random module to generate unpredictable numbers, and try except to safely handle invalid input without crashing the program. This is a great example of how simple Python tools can come together to create an interactive and user-friendly application. Try changing the number range, adding difficulty levels, or improving the messages to make the game your own. Great work. See you in the next lesson. Now let's zoom in on what we're actually going to build. When the program runs, it starts by showing the project name in the terminal and asking for input. For example, enter time in seconds 5. Once the user enters a number, the screen updates every second, showing messages like time remaining 5 seconds, then 4, 3, 2, and 1. When the countdown finishes, it prints time's up, and then asks, start another timer? If the user chooses no, the program ends politely. While building this, you'll practice several core Python concepts. You'll use input to receive data from the user and store it in variables. You'll use a while loop to repeat actions until the timer reaches 0. You'll rely on the time module to pause the program for 1 second at a time, and you'll use if conditions and try except blocks to handle invalid input safely without crashing the program. This project is a great example of how even beginner-level Python can solve everyday problems. By the end, you'll have a program you actually understand and can reuse or improve on your own. In the next step, we'll walk through the code piece by piece and build this countdown timer together step by step. Next, let's take a look at the structure of this project, starting with the countdown timer function. This function is where the main behavior of the timer lives. When it runs, it first prints the program title so the user knows what's happening. Then it asks the user to enter a number of seconds and stores that value so the program can work with it. This is where user input and variables come together in a very practical way. Inside this function, we're preparing everything the timer needs before the countdown even starts. We leave the input, convert it into a number, and make sure the program has the data it needs to continue. By isolating this logic inside countdown timer, we keep the code clean, readable, and easy to reuse. This structure is important because it separates responsibilities. The timer logic stays inside one function, while the overall program flow is handled elsewhere. That makes the program easier to understand, especially as it grows. In the next step, we'll build on this foundation and start adding the actual countdown behavior so the timer can tick down 1 second at a time. Now let's focus on the main function that actually makes the timer work. Inside countdown timer, everything starts by asking the user to enter a number of seconds. That input is immediately converted into an integer, so Python can perform calculations with it. To keep the program safe and beginner-friendly, this step is wrapped in a try block, which means the program won't crash if the user types something invalid. Next, the function checks whether the number entered is a positive value. If the user enters 0 or a negative number, the program prints a clear message and stops the timer early. This helps prevent logical errors and keeps the behavior predictable. Once the input is valid, the countdown begins. A while loop runs as long as the number of seconds is greater than 0. On each loop, the program prints how much time remains, pauses for 1 second using the time module, and then reduces the remaining time by 1. This creates the real-time countdown effect you see in the terminal. When the loop finishes, the function prints a final message to let the user know the countdown is complete. If at any point the input can't be converted into a number, the accept block catches the error and displays a friendly message instead of showing a confusing error trace. That's it for this project. In this lesson, you built a simple but very useful countdown timer that runs right in the terminal. The program asks the user for a number of seconds, counts down in real time, and clearly lets the user know when the time is up. It's a small project, but it solves a real everyday problem and feels like a complete application. Along the way, this project demonstrates several core Python concepts that beginners need to master. You used input and variables to receive and store user data. You worked with a while loop to repeat actions until a condition was met. You used the time module to pause the program and create a real-time effect. You also practiced if conditions and try except blocks to handle invalid input safely and prevent crashes. Try experimenting by changing the messages, adding minutes instead of seconds, or improving the display. Great job. See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is to help users find their correct age by entering their birth year, month, and day. When the program runs, it starts by showing a clear title on the screen. It then asks the user to enter their birth year, followed by the birth month and birthday. After that, the program immediately displays the calculated age. For example, if the user enters 2000 for the year, one for the month and one for the day. The program will respond by showing the correct age based on today's date. After displaying the result, it asks whether the user wants to calculate again, making the app feel interactive and easy to use. As we build this project, you'll practice several important Python concepts. You'll work with input to collect data from the user, variables to store values, and type conversion to turn text into numbers. You'll also see how conditional logic is used to check whether a birthday has already occurred, how loops allow the program to repeat, and how error handling keeps the program from crashing when the user enters something invalid. In the next step, we'll walk through the code one part at a time and see exactly how this age calculator is built from start to finish. Now let's take a look at the structure of this program and understand how everything is organized. At the top, we start by importing what we need from the datetime module. This gives the program access to today's date, which is essential for calculating age accurately. Right after that, the main logic is placed inside a single function that handles the age calculation. This function is responsible for showing the title, asking the user for their birth year, month, and day, and later displaying the result. Keeping this logic in one place makes the code easier to lead and easier to reuse. Below that, we have a main control function. This part of the program acts like the engine that keeps everything running. It uses a loop so the age calculation can run again and again without restarting the program. After each calculation, the user is asked whether they want to continue or exit. If they choose to stop, the loop ends and the program finishes cleanly. Finally, at the bottom, there is a small entry check that tells Python where the program should start running. This ensures the main control logic runs only when this file is executed directly. This structure is simple but very powerful. It separates responsibilities clearly, keeps the code readable, and helps you build good habits for larger programs later on. In the next step, we'll zoom in on the age calculation logic itself and see how the program turns a birth date into the correct age. Now let's focus on the main function, where the real work of this program happens. Once the birth date is collected, the program creates a date object for that birthday and another one for today's date. It then calculates the age by comparing the 2 years. But it does not stop there. The program also checks whether the birthday has already happened this year. If it has not, the age is adjusted by subtracting 1, which is what makes this calculator accurate instead of approximate. You can see this clearly in the examples on the right. When the birthday has already passed, the program shows a higher age. When the birthday is still coming later in the year, the program correctly shows 1 year less. This small check makes a big difference in real-world accuracy. This function also includes error handling. If the user enters something that is not a valid number or an impossible date, the program does not crash. Instead, it displays a clear message asking the user to enter a valid date. This makes the app more user-friendly and more reliable. That's it for this project. In this lesson, you built a simple but practical age calculator that helps users find their correct age by entering their birth year, month, and day. Instead of guessing or doing mental math, the program uses today's date to give an accurate result every time. Through this project, you practiced several core Python concepts that are essential for beginners. You worked with user input to collect data, variables to store values, and type conversion to turn text into numbers. You use conditions to make decisions, loops to repeat the program, and error handling to deal with invalid input safely. You also learned how to work with dates using a built-in module to solve a real-world problem. This is a great example of how small pieces of Python can come together to create something useful and reliable. Try changing the messages, adding extra checks, or expanding the program in your own way. Great work. See you in the next lesson. Now let's zoom in on what we're actually going to build. In this project, we're creating a file lister, a simple but very useful console program that helps you see what's inside any folder on your computer. The idea is straightforward and beginner-friendly. The program asks the user to type in a folder path, then it looks inside that folder and shows everything it finds. Each item is clearly labeled so you can tell whether it is a file or a folder, and the program also handles common problems like entering a path that does not exist or one you do not have permission to open. When you run the program, you'll see a clean prompt asking for a folder path. For example, you might type something like a downloads folder path. After you press enter, the program prints a list on the screen. You might see output like a folder named Photos, a file named Report PDF, a file named Music MP3, and another folder named Projects. Everything is displayed line by line so it is easy to lead and understand. Along the way, this project introduces several core Python ideas. You'll practice using input to get information from the user, variables to store paths and file names, and a loop to go through each item in a folder. You'll also learn how Python can work with the operating system to lead folders, and how try and accept help your program respond safely when something goes wrong. In the next step, we'll walk through the code in detail and build this project together from start to finish. Now let's take a moment to understand the overall structure of this file lister program and how the pieces fit together. At the very top, the program imports the OS module. This gives Python access to tools that let it work with folders and files on your computer. Everything related to reading folder contents depends on this module. Next, we define the function that handles listing files. This function has a clear responsibility. It prints a title so the user knows the program is running, then asks for a folder path and stores that input. At this stage, the function is focused only on collecting the path and preparing to work with it. Keeping this logic inside its own function makes the code easier to lead and reuse. After that, we define the main function. This function controls the flow of the entire app. Inside it, a loop runs continuously, calling the file listing function each time. This means the user can check one folder, then immediately check another without restarting the program. Once the file listing function finishes, the program asks the user whether they want to list another folder. The input is converted to lowercase so the program can handle different typing styles. If the user chooses not to continue, the program prints a short goodbye message and exits the loop cleanly. At the very bottom, there is a small but important check that starts the program. This ensures that the main function runs only when this file is executed directly. It keeps the code organized and prevents it from running automatically if it is imported elsewhere. Next, let's create the logic of listing files. Now let's take a closer look at the main function and see how the core logic of this program really works. Let's look at the try block. This is where the program attempts to lead the folder using the operating system tools. When the program calls the directory listing command, Python tries to fetch all items inside the given path. If the folder exists and is accessible, the program receives a list of file and folder names. The program then checks whether that list is empty. If there are no items inside the folder, it prints a clear message saying the folder is empty and exits the function early. This keeps the output clean and avoids running unnecessary code. If items do exist, the program prints a contents label and starts a loop. This loop goes through each item one by one. For every item, the program builds a full path by combining the folder path and the item name. This step is essential because Python needs the full path to correctly identify what each item is. After creating the full path, the program checks the item type. If it is a file, it prints the name with a file label. Otherwise, it prints the name with a folder label. This simple check is what makes the output easy to read and useful at a glance. If something goes wrong during this process, the accept block takes over. If the folder cannot be found, the program prints a friendly message telling the user to check the path. Instead of crashing, the program recovers smoothly and waits for the next action. That's it for this project. In this lesson, we built a simple file lister app that helps you explore what's inside a folder on your computer. Instead of opening folders one by one, this program gives you a clear list of files and folders right in the console. Through this project, you practiced several important Python concepts. You worked with user input to collect information, variables to store values, loops to repeat actions, and condition checks to make decisions. You also learned how to use a module to interact with the operating system and how try and accept help your program handle errors safely. This is a great example of how a small amount of code can solve a real problem and make your programs more practical. Feel free to experiment by improving the output or adding new features. Great work. See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is simple and practical. It allows users to choose an operation from a menu and calculate things like square roots and power values, all from the terminal. Instead of stopping at add or multiply, this calculator shows how Python can handle more advanced math in a clean and safe way, even when the user makes a mistake. When the program runs, you'll see a clear menu printed on the screen with numbered options. For example, the user might choose option 5 for square root, enter the number 2, and immediately see the result printed as the square root of 2. Or they might choose option 6 for power, enter a base of 2 and an exponent of 3, and get a result of 8. After each calculation, the program asks whether the user wants to continue, making it feel like a real interactive tool rather than a one-time script. Along the way, this project helps you practice several important Python concepts. You'll use input to collect data from the user, variables to store numbers and choices, and the math module to perform square root and power calculations. You'll also see how loops keep the program running until the user decides to stop, and how try except blocks protect your program from invalid input or runtime errors. If you're just starting out, this is a great step forward. You're not only writing code that works, but code that interacts with users and handles real-world situations gracefully. Take your time, experiment with different inputs, and don't worry about getting everything perfect on the first try. In the next step, we'll walk through the program piece by piece and build it together with a clear step-by-step example so you can fully understand how everything fits together. Now let's look at how this project is structured and how all the pieces fit together. At the top of the file, we start by importing the math module. This gives us access to functions like square root and power, which are key features of this calculator. Next comes the calculator plus function. This function represents one full run of the calculator. Inside it, the program prints the calculator title and displays a menu of available operations. It then waits for the user to choose an option and runs the corresponding calculation logic. Below that, we define the main function. This function is responsible for controlling how long the program runs. It uses a loop to repeatedly call calculator plus, so the user can perform multiple calculations without restarting the program. After each calculation, the user is asked whether they want to continue or quit. If the user chooses not to continue, the loop breaks and the program prints a goodbye message. This gives the application a clean and friendly ending instead of stopping abruptly. Finally, at the bottom of the file, the program checks whether it is being run directly. If it is, the main function is called and the calculator starts running. In the next step, we'll zoom in even further and walk through the calculation logic itself so you can see exactly how user input turns into real math results. Now let's look more closely at the calculator plus function and focus on how the calculation logic works. For basic operations like add, subtract, multiply, and divide, the program first asks the user to enter two numbers. Those values are converted into floating point numbers so the calculator can handle decimals, not just whole numbers. Based on the selected option, the program performs the correct calculation and immediately prints the result. When the user chooses the square root option, the flow changes slightly. Instead of asking for two numbers, the program asks for just one. Before calling math square roots, it checks whether the number is negative. If it is, the program prints a clear message explaining that square roots of negative numbers are not allowed. If the number is valid, the square root is calculated and displayed. The power option follows a similar idea. The program asks for a base and an exponent, then uses math power to calculate the result. This shows how Python's math module can handle more advanced calculations with very readable code. At this point, the program assumes the user enters valid input. There is no error handling yet, and that is intentional. This step helps you clearly understand the core logic and flow of the program before adding extra safety features. In the next step, we'll build on this logic and introduce proper error handling so the calculator can respond safely even when the user makes a mistake. Now let's move on to the error handling part and introduce try and accept, which makes this calculator much more robust and user-friendly. Up until now, the program assumed that the user always entered valid numbers, but in real life, users make mistakes. They might type letters instead of numbers or try to divide by 0. Without error handling, those situations would cause the program to crash immediately. To solve this, we wrap the calculation logic inside a try block. This tells Python, try to run this code normally. If everything goes well, the program behaves exactly the same as before. Nothing changes for valid input. However, if something goes wrong, Python raises an error. For example, entering text where a number is expected raises a value error. Dividing by 0 raises a zero division error. Instead of stopping the program, Python jumps to the corresponding except block. In the accept value error block, the program catches invalid numeric input and prints a clear message asking the user to enter valid numbers. In the accept zero division error block, the program explains that division by 0 is not allowed. This keeps the calculator running and avoids confusing error messages. By adding try and accept, the calculator becomes much more realistic. It can now handle unexpected input gracefully, guide the user, and continue running without breaking. That's it for this project. In this lesson, you built Calculator Plus, a console-based program that lets users perform more than just basic math. Instead of stopping at simple calculations, this app allows users to calculate square roots and power values in an interactive and easy-to-use way. Along the way, this project demonstrated several core Python concepts. You practiced collecting user input, converting values into numbers, using conditional logic to control program flow, working with the math module for advanced calculations, and adding error handling so the program can respond safely to invalid input. This is a solid step forward in your Python journey. Try experimenting with new operations, adjusting the messages, or extending the menu with your own ideas. Great work. See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is to make attendance recording easy and reliable. Instead of writing things down on paper or remembering names in your head, this app lets you enter a student's name, mark their status as present or absent, and automatically save that information along with today's date. You can also view all past attendance records whenever you need them. When the program runs, you'll see a clean menu in the terminal with a few options. For example, you can choose to mark attendance, type in a name like Tom, enter a status such as present, and the program immediately confirms that the attendance has been recorded. If you choose to view attendance, the app neatly displays all saved records, showing the name, date, and status in a clear table-like format. Everything is stored in a CSV file, so the data stays even after the program closes. While building this project, you'll practice several important Python concepts. You'll use input to interact with the user, variables to store names and status, and functions to organize your code into clear sections. You'll also work with a while loop to keep the menu running, use the CSV module to save and read data from a file, and apply basic try-except error handling to make the program more robust. This is a great example of how a small amount of Python knowledge can turn into something genuinely useful. Don't worry if some parts feel new at first, you're learning step by step, and that's exactly how programmers grow. In the next step, we'll walk through a clear step-by-step example of how this program works behind the scenes so you can see how everything fits together. Now let's take a look at the structure of this project. At the top of the file, the program starts by importing the modules it needs. This tells Python which tools it will use, such as handling CSV files and working with dates. Right after that, a constant is defined for the file name, which makes the code easier to manage and avoids repeating the same value in multiple places. Next, you can see several functions grouped together. Each function has a single responsibility. One function prepares the file, another handles recording attendance, and another is responsible for reading and displaying saved records. This separation makes the code easier to lead, understand, and maintain. Below those functions is the main function, which acts like the control center of the program. This is where the flow starts. The file setup runs first, and then a loop keeps the program running so the user can repeatedly choose actions from the menu. Based on the user's choice, the program calls the appropriate function. Finally, at the very bottom, there is a small but important check that ensures the main function runs only when the file is executed directly. This is a common Python pattern and helps keep programs clean and reusable. In the next step, we'll update each function step by step. Now let's look at the initialize file function, which is the very first thing that runs when the program starts. The purpose of this function is simple but very important. It makes sure that the attendance file exists before we try to use it. Without this step, the program wouldn't know where to save attendance data, and that could lead to errors later. When this function runs, Python tries to create a new CSV file using the file name we defined earlier. At the same time, it writes the header row, which includes the column names for the student's name, the date, and the attendance status. This gives the file a clear structure right from the beginning. What makes this function safe is the way it handles errors. If the file already exists, Python raises a file exists error. Instead of crashing the program or overwriting existing data, the code simply ignores the error and continues. This means any attendance records saved from previous runs are fully preserved. From a learning point of view, this function shows how Python can prepare resources before the main logic runs. You're learning how file creation works, why headers matter in CSV files, and how try-except can be used in a real practical situation. Once this setup step is complete, the program is ready to start interacting with the user. After this, we'll move on to the mark attendance function, where we actually collect input and save attendance records. Now let's move on to the mark attendance function, which is where the core action of this app takes place. This function is responsible for collecting attendance information from the user and saving it to the file. When it runs, the program first asks for a student's name. Any extra spaces are removed so the input stays clean. Next, it asks for the attendance status and formats it so values like present or present are handled consistently. Before saving anything, the function performs a simple but important check. If the name is empty or the status is not either present or absent, the program stops right there and informs the user that the input is invalid. This prevents incorrect or messy data from being written to the file. Once the input is valid, the function automatically gets today's date in a standard format. It then opens the CSV file in append mode, which means a new row is added without touching existing records. The student's name, the date, and the status are written as a single attendance entry. Finally, the program confirms that the attendance has been recorded successfully. This clear feedback lets the user know their action worked as expected. After recording attendance, the next step is to look at the view attendance function, which reads this saved data and displays it back to the user in a readable format. Now let's move on to the view attendance function, which is responsible for displaying all the data we've saved so far. When this function runs, the program first prints a clear heading so the user knows they are looking at attendance records. This helps separate the output visually from the menu and makes the results easier to lead. Next, the function attempts to open the CSV file in lead mode. Using the CSV reader, it goes through the file row by row and prints each line in a clean, formatted way, showing the name, date, and attendance status side by side. This allows the user to quickly scan past records without needing to open the file manually. The function also includes basic error handling. If the attendance file does not exist for any reason, the program catches the error and shows a friendly message instead of crashing. This makes the app more robust and user-friendly, especially for first-time use. That's it for this project. In this lesson, we built a simple attendance tracker that helps record who is present or absent and saves that information so it can be checked later. Even though the program runs in the console, it solves a very real and practical problem. Through this project, you practiced several core Python concepts. You worked with user input to collect information, variables to store data, and functions to organize your code into clear sections. You also used loops to keep the menu running, learned how to lead from and write to files using the CSV module, and applied basic error handling to make the program safer and more reliable. This is a great example of how small pieces of Python knowledge come together to create something useful. Try experimenting by adding new features, like searching for a specific name or counting total attendance. Great work! See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is to manage user preferences in a smart way. Instead of losing data every time the program stops, this app can save settings to a file, load them again when it starts, and let users view, change, or reset those settings whenever they want. It's all about making the program remember things, just like real applications do. When you run the program, you'll see a menu appear in the terminal with options like viewing current settings, changing a setting, resetting everything back to defaults, or exiting the app. For example, you might choose to change the theme, type in dark, and the program will save that choice. When you choose the View Settings option, you'll see that the theme is still set to dark, showing that the data was successfully stored and loaded from a file. Along the way, this project uses several core Python concepts. You'll work with input to interact with users, dictionaries to store settings, and JSON files to save data permanently. You'll also see how try except helps prevent crashes when files are missing or broken, and how multiple functions make the code easier to lead, reuse, and maintain. In the next step, we'll walk through the structure of the program and start breaking it down one part at a time so you can see exactly how everything works together. Now let's take a look at the overall structure of the settings manager before we dive into individual functions. At the top of the file, we start by importing the tools we need, such as JSON handling and a clean way to work with file paths. Right after that, we define where our settings file lives and what the default settings should be. This gives the program a clear starting point and ensures it always knows what values to fall back on. Next, you can see that the program is broken into several small focused functions. Each function has a single responsibility, like loading settings, saving them, displaying them, changing values, or resetting everything back to defaults. This structure makes the code easier to lead, easier to debug, and much easier to extend later if we want to add new settings. At the bottom, everything comes together inside the main loop. This is where the menu is shown, user input is received, and the correct function is called based on the user's choice. The program keeps running until the user decides to exit, which is a very common pattern in console applications. The important thing to notice here is that we're not writing one long block of code. We're organizing our logic into clear sections and reusable functions, just like real-world Python programs do. In the next step, we'll zoom in on the first key function, load settings, and see how the program safely loads data from a file and handles errors without crashing. Now let's focus on the first important function in this project, load settings, because this is where everything begins. First, you might notice the function defines dict. This is called a type hint. It doesn't change how the program runs, but it tells us what kind of value the function is expected to return. In this case, it means that the load settings function will return a dictionary. When this function finishes, we expect to get something like a collection of key value pairs, such as a username, theme, volume, and notification settings. Type hints are mainly used to make code easier to understand and easier to maintain. When someone reads this function, they can immediately know what kind of data will come back without reading the entire function body. So even though it's optional and not required for the program to work, it's a good habit to use it, especially in larger or more structured projects like this one. Okay, let's go into the details. This function is responsible for loading the settings when the app starts. The very first thing it does is try to open the settings file and read its contents as JSON. If the file exists and the data is valid, the settings are loaded successfully. An important detail here is that the loaded data is merged with the default settings. This means even if some settings are missing from the file, the program will automatically fill them in with default values. That makes the app much more reliable and flexible. Next, the function handles situations where things don't go as planned. If the settings file doesn't exist at all, the program doesn't crash. Instead, it simply returns a fresh copy of the default settings. This allows the app to run smoothly even on the very first launch. It also protects against corrupted or broken files. If the JSON file cannot be read properly or contains invalid data, the function catches the error, shows a warning message, and safely falls back to the default settings. This kind of defensive programming is extremely important in real applications. By the end of this function, we always get a clean dictionary of settings. In the next step, we'll move on to show settings and look at how the program displays these settings in a clear and user-friendly way. Now let's move on to the show settings function, which is responsible for displaying the current settings in a clear and readable way. This function receives one argument called settings, and you can see from settings, dict that it expects a dictionary. That dictionary contains all the current values, like the username, theme, volume, and notification settings. You might also notice the type hint none at the end of the function definition. This tells us that the function does not return any value. Its only job is to show information on the screen, not to produce data for other parts of the program. Inside the function, we start by printing a header, so the output is easy to recognize in the console. Then we use a for loop to go through each key value pair in the dictionary. The items method lets us access both the setting name and its value at the same time, and each pair is printed on its own line. When the function runs, the user sees a clean list of settings, exactly like in the demo on the right side of the slide. Nothing is modified here, the data is simply read and displayed. This is a great example of a function that has a single, clear responsibility. It keeps the program organized and makes the main menu logic much easier to read. In the next step, we'll look at Save Settings and see how the program writes these settings back to a file so they can be reused the next time the app runs. Now let's look at the Save Settings function, which is the part of the program that makes everything stick. This function's job is to take the current settings and write them into the settings file. Whenever a setting is changed or reset, this function is called so the new values are saved permanently. Inside the function, the file is opened in write mode. This means the existing content is replaced with the updated settings. Then json.dump is used to write the settings dictionary into the file in JSON format. The indentation makes the file easy to read if you open it manually, which is helpful for learning and debugging. What's important here is that this function doesn't decide when to save. It simply saves. Other parts of the program, like set setting and reset settings, call this function when they need to. This keeps responsibilities clearly separated and avoids repeating the same file writing logic in multiple places. Because of this setup, every change the user makes is immediately stored, and the next time the app starts, those settings can be loaded again. In the next step, we'll move on to set setting and see how the program safely updates individual settings based on user input. Now let's focus on the set setting function, which is where the user actually changes values. When the user chooses the option to change a setting, this function starts by asking which setting they want to update. It immediately checks whether that setting exists. If the user enters an unknown name, the function stops early and shows a clear error message. This prevents accidental changes and keeps the program safe. Next, the function asks for a new value. At this point, the program carefully checks the input based on the type of setting being changed. If the user is updating the volume, the input is converted to a number and checked to make sure it's within a valid range. For notifications, the input is interpreted as on or off using common words like true, false, yes, or no. For the theme, the value is limited to allowed options only. If the input doesn't meet the rules, the function catches the problem, prints an error message, and exits without saving anything. This way, invalid data never makes it into the settings file. Once the input passes all checks, the setting is updated in the dictionary and Save Settings is called to store the change permanently. A confirmation message is then shown so the user knows the update was successful. You can see the result in the demo on the right, where changing the theme to dark is immediately reflected when the settings are displayed again. In the next step, we'll look at reset settings and see how the program quickly restores everything back to its default state. Now let's look at the reset settings function, which gives the user a quick way to start fresh. When the user chooses the reset option from the menu, this function creates a new setting dictionary based on the default values. Using a copy ensures the original defaults stay unchanged while the program works with a new, clean set of settings. Next, the function immediately saves these default settings to the file. This means any previous changes are completely replaced, and the settings file now matches the original configuration. After that, a confirmation message is shown so the user knows the reset was successful. This feedback is important because resetting settings is a big action, and the user should always know it happened. Finally, the function returns the new settings back to the main program. This keeps everything in sync, so the menu and other functions continue using the updated values without needing to reload the file. You can see in the demo that after choosing the reset option, all settings return to their original state, and viewing the settings confirms that everything is back to default. With this function in place, the Settings Manager gives users full control. They can view, change, save, and reset their preferences safely and easily. That's it for this project. In this project, you built a simple but practical settings manager that can remember user preferences instead of forgetting everything when the program closes. It lets users view their current settings, change individual values, reset everything back to defaults, and safely save those choices for the next time the app runs. Along the way, this project demonstrates several core Python ideas. You worked with user input and menu-driven programs, used dictionaries to store structured data, handled files with JSON to make data persistent, and used functions to organize logic into clear reusable parts. You also saw how error handling keeps a program stable even when something unexpected happens. This is the kind of foundation that many real applications are built on. So what you learned here will show up again and again in future projects. Great work! Try experimenting by adding new settings or features and see you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this program is to show how Python can fetch real data from an online service, display it clearly, and interact with the user. When the app runs, it asks an online joke service for a random joke, shows the setup first, waits for the user, and then reveals the punchline. After that, the user can decide whether to see another joke or exit the app. Here's what it looks like in action. You run the program and the console prints a title like random joke followed by a question. The program then pauses and asks you to press enter. Once you do, it prints the punchline. After that, you're asked if you want another joke by typing Y or N, and the program responds based on your choice. While building this app, you'll work with several important Python ideas. You'll use input to interact with the user, variables to store data from the internet, and a loop to let the program run again and again. You'll also see how Python can make web requests using a module, how to lead data returned from an API, and how try and accept help the program handle network errors safely without crashing. This is a great example of how even a small program can feel interactive and real. You're not just printing text, you're building something that responds to the user and connects to the outside world. Take your time with it, enjoy the process, and don't worry if everything doesn't click immediately. In the next step, we'll walk through the code one piece at a time so you can see exactly how this app works from start to finish. Now let's take a look at the overall structure of this program and understand how everything is organized before we dive into the details. At the very top, the program starts by bringing in a module that allows Python to talk to the internet. This is what makes it possible to fetch jokes from an online service instead of using fixed text. Next, you'll see a function that is responsible for getting and showing a joke. Right now, we're just defining its place in the program. Think of this function as a box where all the joke-related logic will live. We are not opening that box yet, but we are clearly marking where it belongs. After that comes the main control function. This is where the program flow is managed. Inside it, a loop keeps the app running again and again. Each time the loop runs, the joke function is called, a joke is shown, and then the program asks the user a simple question about whether they want to continue or not. If the user chooses yes, the loop keeps going and another joke appears. If the user chooses no, the program prints a short goodbye message and stops cleanly. This makes the app feel interactive and polite instead of suddenly ending. Finally, at the bottom, there is a special check that tells Python where the program should start running. This ensures that the main control logic only runs when this file is executed directly. This structure helps keep the program easy to lead and easy to extend. Each part has a clear responsibility and nothing feels mixed together or confusing. In the next step, we'll zoom into the joke function itself and break down exactly how it fetches a joke, handles errors, and displays the setup and punchline step by step. Now let's zoom into the heart of this app and look at the function that actually fetches and shows the joke. This function is responsible for one clear job: getting a random joke from the internet and presenting it to the user in a fun and readable way. It starts by storing the web address of a public joke service. This address is where the program sends a request whenever it needs a new joke. Next, the program tries to connect to that address. This is done carefully, with a time limit, so the app does not freeze if the network is slow or unavailable. If the connection does not succeed or the server does not respond correctly, the function stops early and shows a simple message instead of crashing. When the connection is successful, the response comes back as structured data. The function converts that data into something Python can work with, in this case JSON style, and then pulls out two important pieces: the setup of the joke and the punchline. These values are stored in variables so they can be used later. After that, the program prints a short title and displays the setup first. It then pauses and waits for the user to press enter. This pause creates a natural break, just like telling a joke in real life. Once enter is pressed, the punchline is printed to the screen. Finally, if anything goes wrong during the connection process, the function catches the problem and shows a friendly network error message. This makes the app more reliable and beginner-friendly, even when something unexpected happens. That's it for this project. In this lesson, you built a simple but practical Python app that connects to the internet, fetches a random joke, and displays it in a fun, interactive way right in the console. Through this project, you practiced several important Python concepts. You used functions to organize your code, variables to store data from the internet, and input to interact with the user. You also worked with loops to repeat actions, learned how Python communicates with an API, and saw how try and accept help handle network errors safely without stopping the program. This is a great example of how even a small project can feel real and interactive. Try changing the messages, adjusting the flow, or exploring a different API to make it your own. Great work. See you in the next lesson. Now let's zoom in on what we're actually going to build. The goal of this app is simple and practical. The program asks the user to type in a city name, connects to an online weather service, and then shows the current temperature and weather condition. Instead of working with fake data or hard-coded values, you'll be working with real-time information, just like professional applications do. When the program runs, it starts by showing a clear prompt asking for a city name. For example, the user might type London. After that, the app responds by displaying the city name, the temperature in Celsius, and a short description such as overcast clouds or clear sky. Once the result is shown, the program asks if the user wants to check another city. If the user types Y, they can enter a new city like New York or Tokyo. If they type N, the program ends with a friendly goodbye message. As you build this project, you'll practice several important Python concepts. You'll use input to get data from the user and store it in variables. You'll use a loop to allow the program to run multiple times without restarting it. You'll learn how to send a request to an online API with API key and handle the data that comes back. You'll also see how try except helps protect your program from network errors or invalid input. This project is a great step forward because it shows how Python can interact with the real world. You're not just learning syntax, you're building something useful and realistic. Take your time, follow along, and don't worry if everything doesn't click immediately. In the next step, we'll walk through the code piece by piece and build this weather checker together step by step. Now let's take a look at the overall structure of this program and how everything fits together before we dive into the details. At the very top, the program starts by importing a module that allows Python to talk to the internet. This is what makes it possible to send a request to a weather service and receive real-time data. Right after that, we prepare a place to store important configuration values, such as the API key and the base address of the weather service. Keeping these values near the top makes the code easier to lead and maintain. Next, the program defines a function whose role is to handle one complete weather check. This part is responsible for asking the user for a city name, sending the request, and displaying the result. By separating this logic into its own function, the program stays clean and easy to understand. Below that, there is a main control function that manages the flow of the app. Inside it, a loop keeps the program running so the user can check the weather for multiple cities without restarting the app. After each check, the program asks whether the user wants to continue or exit, and it responds accordingly. Finally, the program includes a small entry point that tells Python where to start running the code. This ensures the app behaves correctly when it is executed. In the next step, we'll focus on getting the API key and understanding why it is required before we can fetch real weather data. Now let's talk about one of the most important pieces of this project, getting the API key and setting it in your code. An API key is like a personal access pass. When your program asks the weather service for data, it needs a way to prove who is making the request. Without this key, the service will simply refuse to send any weather information back. To get the key, you first sign up on the OpenWeather website. After creating an account, the site gives you a unique API key. This key belongs to you and tells the weather service that the request is coming from a valid user. Once you have the key, the next step is to place it into your Python code. Now that we have the API key, the next step is to set it directly in our code so the program knows how to authenticate itself. Here we store the API key in a variable near the top of the file. This is intentional. By keeping it in one clear place, the program becomes easier to lead and easier to update later. If the key ever changes, you only need to replace it once instead of searching through the entire code. Right below that, We also keep the base address of the weather service. It's also called endpoint. Together, these two values act like the foundation of our app. One tells Python where to send the request, and the other proves that the request is allowed. When the program runs, these values are not shown to the user. They work quietly in the background, making sure every request is properly formed and accepted by the weather service. This is a common pattern you'll see again and again in real-world Python applications that use external services. With the API key now set and ready to use, the program has everything it needs to start communicating with the weather service. In the next step, we'll move on to the function that actually asks for the city name, sends the request, and displays the weather result to the user. Now let's focus on the heart of this application, the function that actually checks the weather and shows the result to the user. This function starts by displaying a clear title in the console and then asks the user to enter a city name. The input is cleaned by removing extra spaces, which helps prevent simple input mistakes. Right after that, the program checks if the user entered anything at all. If the input is empty, it stops early and shows a clear message instead of continuing with a bad request. Next, the function prepares the data needed to talk to the weather service. This includes the city name provided by the user, the API key we set earlier, and the unit setting so the temperature is returned in Celsius. All of this information is grouped together and sent as part of the request. The program then sends a request to the weather service and waits for a response. If something goes wrong, such as an invalid city name or a problem with the API key, the function handles it gracefully and explains the issue to the user instead of crashing. When a valid response comes back, the function reads the data and pulls out only what we need. It extracts the temperature from the main weather data and the condition description from the weather section. Even though the response contains a lot of information, we focus only on the most useful parts for this app. Finally, the function displays the result in a clean and readable format. The city name, temperature, and weather condition are printed clearly, so the user can understand the output at a glance. If a network problem happens at any point, the function catches it and shows a friendly error message. That's it for this project. In this project, you built a simple but practical weather checker app using Python. The program lets a user type in a city name and instantly see the current temperature and weather condition using real-world data from an online service. Along the way, this project demonstrated several core Python concepts. You used input to interact with the user and variables to store data. You worked with functions to organize logic and a loop to allow the program to run multiple times. You learned how to send requests to an external API, lead structured data from a response, and handle possible errors so the program does not crash. This project is a great example of how Python can connect to real-world services and produce useful results, even with simple code. Try changing the output, adding more details like humidity, or experimenting with different cities. Great work! See you in the next lesson.